Hi everyone, this is Quantum Computing Fundamentals uh, class session 7, part 2 of the quantum computing gates, circuits, and maybe you can call it even algorithms. This is Prakash. Today it's July 17th, Monday night, and I'm recording part 1 of the uh, program. So we had said that we'll complete June, July, August, September into 4 parts. Quantum fundamentals we covered in the first 6 sessions. Now, on the seventh session, we are starting with quantum circuits, and this is also a time to recap what we did earlier and ensure that we have a proper understanding before going into the quantum circuits algorithms, both computer and communications. So let's start this week with This week actually will cover quantum register, quantum data processing, entanglement and build states, and EPR paradox. The part 2 will take later. At this time, I will just leave it at that. Okay. Now, let's start recapping first. What we had seen the last time was about the tensor product. And tensor products, obviously, it's a vector space. So you look at here, it's a vector space for studying composite systems. So you have a system A of qubit 1, you have a system B of qubit B, and a composite system AB is inclusive of both these uh, qubits. So it's a studying of the composite system. So basically, what we are saying is tensor product is a vector space which includes which helps us study the composite systems. System A and System B in this case, System A being the qubit 1, System B being qubit 2 or qubit 2, which is System B. And you can see that nucleus is there, the atom is there, the electron is in zero state or the ground state, and the one state, which is at the outer um, periphery. Now, this is discrete levels. Obviously, there can be more, but let's assume this is a hydrogen atom and it has only two states, and we can have a 0 and 1 state. So the qubit has this qubit has an electron, this qubit has an electron. Both of them have each one electron, and the composite system is what we study using tensor products. Now, there is a difference between tensor product and the product state. Product state is a state vector. So the state vectors are what? Ket0, Ket1 are state vectors. So there are many states. Okay, we are only referring to two states here, spin ups and spin down. Spin up being represented by Ket0, spin down being represented by Ket1. So the ground state to excited state, you can call that way. So there are many such states, and it is not just these two, but there could be many more. But we are not looking at all of them in this. We we have been focused on only the product basically what I call is product state. Uh, in this case, Ket0 and Ket1. These are the state vector we have been focused on. But it doesn't mean that there will not be other state vectors. So state vectors that inhabit the product space, most state vectors in product space are not product states. What it means is they are not the basis states. There are some combination thereof, but states which are relevant to us, which we call as product states, are nothing but basis states. So we only are focused in on the till now at least on the superposition, which is based on the resolvable or factorable to simpler states, which are product states. So in this case, we can say a qubit 1, which is representing system A, can be shown as a linear combination of the coefficients of with respect to the basis states or product states. So the product state alpha 0 ket 0 plus alpha 1 ket 1 is the uh, one which is represented belonging to Hilbert space. Now the 3H will haunt you, but remember Hilbert space is related to vectors, is a virtual or a hyperspace where you are studying the uh, qubit, and it is two dimension. So we have got a qubit which has two dimension, and it is Hilbert space, and it's represented by ket. So you can say in this case h1, yeah, but that is only nominal. You don't have to really call it h1. H of dimension 2 is also fine. H of dimension 2 is fine, but we are just referring as h1 h2. So if you have two systems, the combination of the two can be represented by a tensor product. So whatever h dimension 2 or C2, in this case we call it as complex, because these variables are complex, alpha 0, alpha 1 and beta 0, beta 1 of the two respective qubits are system A and system B. And if you do a cross product, which is the tensor product, we call it, uh, not cross product, sorry, it's tensor product. When you do a tensor product of the two, you arrive at a space which is 4 dimension, and that's same thing can be represented in a little bit different way, in the sense that here you can say alpha 0 and 0. That means if you are representing a state called composite state of 0 and 0 of these two, that is 0 of the left and 0 of the right, or 0 of A and 0 of B, then it becomes alpha 0 0 ket 0 0. Same way alpha 0 1, 0 of this and 1 of that, 1 of this, 0 of this, and so on and so forth. So you can say alpha 0 0 ket 0 0 plus alpha 0 1 ket 0 1 plus alpha 0 1 0 ket 1 0 plus alpha 1 1 ket 1 1. That represents your 4 dimensional Hilbert space, and what applies to 2 dimension applies to 4 dimension, very similar way, no different. So if you have a u, if you have u plus u1 plus u2, similarly if you have v, get v and v1 plus v2, then this combination, uh, what we need to do is we need to do a product of the two. So u1 plus u2 into v. So if we represent uh, here u and v, then you get a u cross u tensor product v. But if you have u1 plus u2 and v, then it will be nothing but u1 plus u2. It's a scalar basically, combination of, same way with if it is u and v1 plus v2, so we can do this way. So essentially tensor products, to remember, is a vector space for studying composite system, and a product state is a state vector. So the product state ket 0, ket 1 of system A and system B both are the state vectors, uh, which are also uh, called as product space, in the product space. State vector in the product base are basis, and all are not basis uh, state vectors. That is the important part. There may be more state vectors which are, uh, we call it entangled, we'll come to that. But at this time, we are only talking of the factorable states. Okay, that's the tensor product. So tensor products helps us in studying the system A and B. Let's go to continue further. Here the same thing I have described with Hilbert space, complex space C2 into C2. So it becomes, so what is the Hilbert transform deals with. What Hilbert transform does, so we talked about uh, Hilbert spaces, and um, so there are three H's I said which will get you in. One is the Hadamard matrix, another is the um, Hilbert space associated with the uh, what do you call the two dimension 2 to the power m dimension vector spaces, which deals with the rotation pi by 2 radians, basically plus minus pi by 2 radian rotation of phase. That is what Hilbert space deals with. But since we ignore the phases, it doesn't impact us right now. So the third one is the um, Hilbert space is one related to the transform. Then there is a Hadamard gate, which is related to the matrix, which deals with the amplitude. This deals Hilbert's deals with the what you call the rotational aspect, phase aspect. So the amplitude aspect, the phase aspect, and then there is a matrix, self-adjoint matrix, which is Hermitian. So you have confusion of the H's here. Three H's are there. Hermitian deals with the adjacency of the matrix. Hilbert's space deals with the what you call the rotational aspect of it, and the Hadamard, which we'll study, will deal with the uh, you can see the Hadamard transfer deals with the what you call uh, uh, the representation in terms of what you call as uh, a transformation which transforms the basis from one to another. In this case, we have seen 0, 1 basis. So if your state product space basis is changed, that is the Hadamard portion of it. So remember the three H's, which are very critical and which will cause a lot of confusion. But so the three Hilbert, one is Hadamard, which we will talk later. But we started with tensor products, and tensor products in space, which is Hilbert space, is 2 raised to m. That is the dimension for n electrons, you can say, or n photons, whatever, particle or wave, whichever way. Particle, wave are different. Particle we deal in terms of electron here, but otherwise, if it is wave theory, then we'll be using Schrodinger equation, which is also nothing but based on some differentiation of space and partial differentiation with respect to time, and then partial differentiation twice with respect to space. So there are some correlations. We don't get into too many integrative details, but here we have to show that tensor products helps us in arriving at the uh, study of composite systems with like example, you remember here ket 0 and ket 0 of space 1 and space system A and system B can be looked as either as ket 0 or can be written as 0 0. So basically we try to not put the tensor space all the time to simplify our notational. Otherwise, ket 0 tensor product of ket 0 is equal to ket 0 equal to ket 0 0. These are treated equal. Same way 0 1 0 1 0 1. So essentially what we have to remember is whatever notation we adopt, they are representing multiple systems. Each electron represents here a qubit, and system A, system B, system C, you can whatever abstract name you call, but most popular is either a binary or decimal. So 0001 or using the number 101, that's the tradition. Now let me go to the uh, bit flip, which is if you have a We have studied the polymetrics X earlier. You remember that X is 0, 1, 1, 0 in this way, or if you go this way vertically, it is 0, 1, 1, 0. Either way, it's so if you have a gate X, if you have an input which is linear combination of this state vector or product space, what we call, uh, which is ket0 and ket1, and if you do a linear combination of alpha 0 ket0 plus alpha 1 ket1, X is a operator, and you know that operator transforms the vector from one to another state, and that is nothing but here alpha 1 ket0 plus alpha 0 ket1. So qubits have both amplitude and phase. So we are talking about bit flip here with the amplitude remaining unitary, because we have said that in quantum physics all gates, all units are normalized and they are unitary. And the other portion is phase flip. So with this we have done the calculation already by substituting x0110, and we know that the spin up is 10, which is this is 1, this is 0, and spin down, this is 0, this is 1, for the same thing. But one is for ket1, that is spin up and spin down, and if you calculate, it comes out to be opposite of it. So you start with a ket0, multiply by the operator x, or not yeah, in this case we are using matrix multiplication, equivalent of what we do in tensor product. So if we do that, then we tend to get a, so on matrix representation we are able to arrive that x gate flips the bits from 0 to 1, 1 to 0. Also you can say ket x, dagger x, x equal to x dagger equal to identity or equal to x square. So what it means that any quantum gate, in this case we call it X gate or Poli-X, it is first of all unitary. Second, if you do a unitary means what? Unitary means if the conjugate, complex conjugate of the transpose is multiplied by the matrix itself, it is equal to identity matrix, and vice versa. That is, if you have a matrix and you take a complex conjugate, and because they have to be in the order, Kidbra order, so it is the identity matrix, or you can say x square equal to I. So this is unitary. It is plus it also satisfies the therefore the XX dagger equal to identity matrix. So unitary matrix we had defined as one when you take a complex conjugate transpose of the matrix, so unit matrix diagonal with 1 1 on the diagonal of it, and that's what we do. So coming back to now phase flip. So the other things which we have been ignoring, kind of thing, saying that hey, phase doesn't matter. Yeah, sure. If you rotate a vector in the vector space of unity circle, which is always ending in unity by transforming, then the phase you may be able to ignore at this time because we are more interested in amplitude. However, you must note that the poly Z matrix which we studied earlier, if you take a linear combination of the alpha 0 ket 0 plus alpha 1 ket 1, if you do a poly Z transform, and you arrive at something new which is alpha 0 ket 0 minus alpha 1 ket 1, and this can be proved easily because you have the Z matrix which we already have taken, and Z of ket 0 is nothing but 1 0 0 minus 1, which is the Z, multiplied by the spin up, which is 1 0 column, and if you multiply you will get 1 0, which is nothing ket 0. So if you multiply a ket 0 by Z, it is maintaining 0, and if you multiply by 1, it is now flipping the bit. The only difference is For a z ket 0, it gives ket 0. For z ket 1, it is reversing the polarity. And that is, it is showing z1 as minus 1, ket 1, minus ket 1. So what it means that this is a phase flip. So if you apply Z transform or poly-Z matrix, it will give you a phase flip. And it also is one of the unitary quantum gates, or you will find that Z complex conjugate of Z multiplied by Z is equal to Z multiplied by complex conjugate of Z is equal to identity matrix. This is same principle as the other one, and Z square. So essentially what we have got from this, mm, yeah. So we will go with this, and then yeah. So let's go with the h equal to 1 by root 2 ket 0 plus minus 1 by root 2 and z of plus. So here is another sample of applying z, and that is, if you have a plus uh, and if you represent plus as 1 by root 2 ket 0 plus 1 by root 2 1, then z of sorry yeah, if you apply a z transform to plus, you will get a minus. So, and whereas if you apply a z to the minus, you will get a plus. So this is also showing that for the z transform, you can apply this flip. So what essentially means is, if you have a when you have a ket 0 ket 1, you are with the z measurement is with respect to z. When you do measurement with respect to plus minus, you can obviously correspondingly, which is nothing but a rigid rotation of the space. If you take a xy axis at 90 degree and say a vector at 45 degree, and if you rotate it, uh, the rotation is a solid rotation. It is in the xy plane only, I'm talking circle. When you rotate it, the vector, if you position with respect to 45 degree as the angle for um, the the projections for x and y. So x and y along with the vector rotate into next uh, 45 degree space, and that is 45 degree, you get the sine cos 1 by root 2. Only thing is, one of them goes plus, one of them minus. That's what is represented here. So I'll move on to the next Hadamard transform. Hadamard transform is it actually if you have a arbitrary input vector, and if you use superposition of them, then what you will get is you will get a transform which is multiplication factor of 1 by root 2 1 1 1 minus, you can put 1 by root 2 outside, and 1 1 1 minus 1. That's what the matrix happens to be. If you take a Hadamard same way transform of this, which is like your x and x and y z and z, Hadamard transform also satisfies the identity matrix. That means it is unitary. And not only that, the only thing which you will observe, that if you feed a ket 0 to it, you get a plus. That means this is the one I was talking about, rotational aspect of it. So it is rotating the face. So basically, it is whatever you represent in 0 and 1 space. If you apply Hadamard transform to any of these product space or vector space vector, then state vector, then you will get a transformation of basis. So if you want to transform basis, from 0 1 to plus minus, you should apply a Hadamard transform. And this is nothing but is the algorithm where if you have mth hm in the m space, obviously this question is what is m? It is 2 to the power m. So if you have m, if you have 0, then h0 is standard defined as 1. H1 is defined as h, which is this matrix. And hm, the m, if m is greater than 1, so if m is greater than 1, let's say if it is 2, then h2 equal to h1 plus h2 minus 1, which is h1. So h1 into h1. So h1 is h. So this, if you multiply it twice, you will get the transformation. So that's what you can say here. Using matrix multiplication, what we are doing is ket0. We know that ket0 into Hadamard, if you take, then uh, this ket0 is represented by 1 0, and this is the matrix. You multiply and you get 1 by root 2, which is nothing plus. Same way, if I take a plus 1 and do a Hadamard transformation on it, you will get 0 1 and you'll get minus. So basically, if you want to transform from 0, ket0, ket1 representation z basis to let's say x basis, then you apply the Hadamard transform. That's what it is indicating, and that's what it is shown. So we have seen Hadamard transform, we have seen bit flip, phase flip, tensor products. So we are left with now unitary matrix. So we must look at uh, qubit first. So if you have a qubit, you have a transformation applied. We know that unitary means if you have a time t and t, if you apply unitary, then there is a time difference, and at time t1, t0 and t1, it is going to be some different thing. So what is that different in quantum? If you have only one qubit gate, all it does is the phase we can ignore. If we ignore the phase, it's nothing but an identity matrix in a because the angle changes, it rotates. And now in terms of rotation, if you have a product space, that is if it is a factorizable state space, state vector, then in that case you are going to get a identity for the multiplication. So this is nothing but unitary matrix, that means. And if you even describe and you want to calculate, you can try it out. There is a sample example in our this one. So if you put a B C D and you have u plus a b c d, you multiply, then you can get a alpha 0, alpha 1 being the coefficient here, alpha 0 prime, alpha 1. So this is the result shown as in algebraic term. Same way, if you have, what is the dimension of 2 qubit gate? So 1 qubit gate, the dimensions was 2 uh, product space or 2 space state vectors, ket0 and ket1, which are what you call, which can be applied in terms of superposition. Same way, if you have 2 qubits, you have 4 states, and that depends on the 0 0 0 1 1 0 1 1, as we said earlier. And if you apply unitary, it should also produce similar matrix of 4. So what it means is you got a unitary matrix 4 by 4, and if you um, subtract the output from the input with a unitary, that's what will say that they are uh, just the transforms, unitary transform. So nothing has changed basically, except of course phase, which we don't take, we don't note in the unitary portion of it. So it's a unit matrix, and you transfer and you still get a unit matrix. So u dagger or u dagger u is equal to I. That's what is for 1 or 2. It's only the dimension change. Otherwise, and plus dimension change plus the, if you have 2 dimension, then you got a column of 2. When you got 4, when you got 2 qubits, then you got a dimension of column vector of 4. So the column vector representation will keep on increasing. If you have 2 to the power 3, which is 2 to 4 to 8, then there will be 8 column vectors. So every state representation of a qubit The more the number you bring in composite, it will contain so many uh, column entries. So now let's get to the quantum register. So quantum register is nothing but a group of bits. In classical, what we do, we have a group of bits, we call them n bits, and we say, hey, it is 0 to n minus 1 digits. So you say, when you want to compute in terms of binary, you say that whatever the term ai into 2 to the power I. So basically ai n minus 1, an minus 2, a0 into 2 to the power I. So example, if we have this sample example, if I take, if you the for a 4-bit register, the value go from 00 to 111, which is 16 values starting 0 to 15, and the MSB is the 2 LSB. So the left side is the MSB, the right side is LSB, least significant bit, most significant bit. So example, if you have 100, which is 8, we can prove it is 8 by taking 2 to the power. So 0, 1, 2, 3. 2 to the power 3 into 1 plus 2 to the power 2 into 0 plus 2 to the power 1 into 0 plus 2 to the power 0 into 0, it's 8 decimal. So 1000 represents a 8 in binary, in register in terms of classical uh, computer. Same 1 qubit register will require two complex coefficients, A and B, because we know A, B, alpha 0, alpha 1, whatever you call. Um, that's what. So we'll require 2 bytes for the A, which is complex, 2 bytes for B, which is complex. So we require 4 classical bytes for a qubit to represent 1 qubit. So if you have n qubit, you will require n into 4 bytes, which means if you have a C2 into C2 into C2 into C2, if you have 4 uh, qubits, then this requires 2 to the power 4, 16 into 4 bytes per qubit, so that will be 64 bytes. So if you keep on increasing the coefficient, if you have 2 to the power 10, then that means 1 kilobyte. So 1 kilobyte, so that's what it will take for 10 qubits. Suppose it is 100, 10 to the power. So now the question is, how do you keep computing if the number of qubits increase? So this is the problem of classical computing. It will require so much storage for a 10 to the power 10 if I take, then that will go to Yoda bytes or something. In fact, millions of Yoda bytes. So megabyte, gigabyte, terabyte, petabyte, zettabyte, and then uh, it will go to another 4 times 10 to the power 4, or another level, which will be of the Yoda byte type. So the more the qubits, more the requirement, and this is unsustainable as far as computation is concerned. So basically quantum scores over this. That's what we want to show. So if you have classical bit 1, 2, 3, 4, 5, 6, 8 up to 16, we are seeing the qubits, the register represented by 1 bit here. Qubit is represented by electrons, so you have 8 electrons, 16 electron, whereas the classical register value, it gets to 256 kilobyte just for a 16 qubit. So you can imagine, and this keeps on going. If you go to the n to the power, to the qubits, n qubits, 2 to the raised to n, then so many will require. And therefore, the basis vectors keep doubling as we go to n, are 2, 4, 2 to the power 3, not doubling, but exponentially raising 2 to the power n. And so basis vectors that are required, 0, 1, 0, 0, 1, after some time it is difficult to write in decimal, so we start writing in binary, we start writing in decimal, so you can keep on going like in 2 to the power n minus 1. So n qubit register and associated Hilbert space, as well as um, Hilbert space also, and the basis vectors also keep increasing. So we have to talk about what is quantum data processing. So let me focus on quantum data processing. So what is the relation between storable values in a 4-bit classical register? So we have said that we need 15, right? 0 to 15, which is 16 values, and that corresponds to that you are going to have um, the basis 10 basis 10 we will have accordingly the register table. So this is just a representation for 16 we had done previously for 2 to the power n. So 16 we had taken here 256k. So it might keep on going. That's why there are something which is important in data processing, and that is relationship between storable values in 4-bit is classical register versus the quantum register. The requirement of memory is pretty high. Plus the bit representation, if you do by bit, is okay for register sake, but for electron it will be 2 to the power n we are getting. So the data processing word, it says quantum parallelism and superposition. So if you have 4 function f0, f1, f2, f3, and if we take it sequentially by classical computing, then we'll do 4 computation. We can also do parallelly to solve fx using threads. Uh, that's one way of doing, which is what the uh, you have found NVIDIA is doing. CUDA, that is Computer Unified Device Architecture, where the device is considered as a periphery to the compute, and but the compute has to manage then the uh, transfer of data or registered data between the memory and the compute. But in quantum computing, what happens is if you do one shot, you describe, only thing is you have to have algorithm before you can do that. So if you can write a fx as some state which is consisting of example like linear combination a0 b1 and c2 using a tensor product, then we can have um, a the coefficients brought out with a function 0 function with ket1 and function with ket1 and ket2 and ket3. So we can solve this problem in one shot, one or more shot. Shot refers to, let's look at shot. So shot is the measurement of qubit in superposition state, which is random. The outcome is either +1 or -1 or 0 or 1, as you may repeat the measurement multiple times to confirmation to get the probability correct. But if it is 50-50, that's what it is. So you may do one shot or multiple shot. Results are averaged out. And so the basic in data processing, what we want to express is power of quantum computing has two specific areas. One, it requires n bit to store 2n dimensional space. So if n is equal to 100, that means 100 electrons can match the storage of 2 to the power 100 dimensional. So basically we are um, way more memory requirement in classical computing. So we'll waste a lot of memory if we use classical computing. So we save a lot in terms of memory. Obviously, the other part of it is the calculation part, because you are doing n calculation in one shot or few shots that may take ages in some other classical way. So therefore, there are algorithms which we can tailor to make them super linear combination of the uh, quantum uh, states, and that is how it is. That is how we can get the quantum data processing. You know. Now let's go on to the results. So results of most quantum computing algorithms will result in a speed as well as saving of memory. Now let's go to entanglement and Bell state. This is the last portion of our thing here. So Bell state is what? Uh, every high dimensional Hilbert space, example in this case H3, H1, H2, which is nominally I am just taking HTH to H1 for a 2 qubit. It's a combination of C2 into C2 and vector H. In this case, if you say H is higher dimension vector H, and if it can be expressed as a linear combination of lower space, which is F and G vectors, then H is equal to uh, vector F in lower space into vector G into lower space. So 2 dimension, or 4 dimension. So this equation, uh, they are unentangled, which is not a special case. If they are unentangled, if they are not entangled, then that means they are following the superposition. That means you can factorize H into F and G. That tells that they are based on the product space, or they are based on the state vector, which are basis vectors, and therefore they will be resulting in a value which is eigenvalue and therefore unitary. They are not entangled. How what happens if you have a if you cannot factorize to lower dimension space? There are some combinations which cannot be, most of them in fact, but we, since based on our factorizable notation, so we say that hey, we can factorize and therefore they are easy to operate on. We can do parallel computation and all that. However, there are more entangled states than the normal states, and especially as we go higher in the dimension, that is if you have multiple qubits. Just for the 2 qubit example, we have 4 Bell states, we call it. They are referred as entanglement. Is that you cannot factorize further. That means you cannot separate a ket 0 from a ket 1. Then that's the problem we have. If you cannot, then in that case it is uh, the function is said to be entangled, or the qubit is said to be entangled, and therefore the vector is supposed to be entangled, all the same. So vector state, whatever you represent functions, whether you talk in terms of particles, whether you talk in terms of wave. In the wave, we should be able to resolve the wave properly in terms of sinusoidal and cosinusoidal, and that's what the Schrodinger equation talks about. Whereas here we are talking in terms of particle electrons, which is again the same thing, but all of them are representative of the spin up and spin down type, either the phase factor being different, that is you have a horizontal polarization or vertical polarization for the light packets, photons, or in terms of electrons. We have looked at it previously. So what we want to say is, if you cannot decompose example, if here is the example, right? Let's say if f is equal to 1 by root 2 of ket 0, ket 1, and g, f and g are 2, and h is equal to the what you call tensor product of f and g, and if you compute this, then you are able to separate out ket 0 0, ket 0 1, ket 1 0, and there should be a ket here which is missing. That's okay, but they are the ket notation. So is this entangled? No, because you are able to take the function, these functions, 2 functions, and resolve it into 4 um, basis space or product space, or state vectors which are known 0 0 0 1 1 0 1 1. They are not entangled. But let's say another vector, let's say 5 plus, which is shown below here. So if 5 plus is product of ket m and ket n, and these are the numbers, and if we find that if we combine this and we get this one, that is equal to 1, we represent them by, normally you will have only one, right? 1 0 0 0 1 0 0 1. So 1 by root 2 of 1 0 0 1. So you got two uh, what you call combination, and they are entangled. If it was 1 0 0 0, we did not have entanglement, but here it is 1 0 0 1, 1 by root 2 of that, and that we had seen previously, that you can entangle provided. So here is the computation which is shown: 5 plus equal to uh, ktem into kten is equal to, as we said, A00 plus A11 and um, B00 and B11. Get, so these two M and N. So if you multiply, you get this, and then product. So basically, A0, A1, A0, B0, A0, B1, A1, B1, and A1, B1. A1, B0, and B0, A1. So if you look at this, so for this to be uh, four equations to be solved, we must have A0, B0 equal to 1, A0, B1 equal to 0, A1, B0 equal to 0, A1, B1 equal to 1. If that is the case, so if you look at the second equation, let's take this second equation, A0, B1 equal to 0. So either A0 or B1, one of them is 0. If that is the case, then it means either A0, B0 equal to 0, because if A0, B1 is equal to 0, one of them is 0. If one of them is 0, then this should be 0, because A0 is 0. That is not true. If you go to the last one, similarly, uh, fourth equation is A1, B1 equal to 1. Whereas the second equation A0, B1 equal to 0. So if B1 is 0, then this cannot be 1. So what it means is, this means either the A0, B0 is 0 or A1, B1 is 0, which contradicts the first or the fourth equation respectively. This means our assumption that phi equal to cat m, uh, tensor product of cat n, is wrong. It is impossible to find m and n such that the tensor products phi plus is a combination, linear combination of cat m and curve. Therefore, it is called entangled. And specifically, there are uh, four uh, what you call vectors. There are vectors which are representing a two-dimensional entangled state. So here are they. So 1001 with 1 by root 2, this equation. Same way phi minus psi plus psi minus. These are very standard in Bell states. They are called entangled Bell states in two dimension. So you can see that once you have unclean one of them, then you have a problem. And especially if they, even though they satisfy the unitary value, that is 1 by root 2 is probability is half, it is half. So they, so if you have a equation linear combination of four where two items are zero, only two items are represented, then it's a problem, and that's what you are seeing in this case. In this combination, these fours are entangled states, as they are called. So with this, I think I will end here. We'll talk about Hadamard gates later, and the EPR also, which is EPR products, which I'll cover in the regular class. Thank you very much, and I'll stop here my recording. Thank you.